Welcome back to the practical session of Understanding Communities through Beta Diversity Concepts and Tools for Applications. In the previous sessions, we have seen concepts of beta diversity, functional redundancy, partitions of beta diversity into its nestedness, turnover components, contribution of species to beta diversity, local contributions to beta diversity, and all other associated concepts of beta diversity. The next objective of the refresher course is to introduce to all of you how to implement the concepts of beta diversity using real life data, how to use these tools to make sense of community data and community information that is collected from the field for research purposes. It does not matter what kind of data we are speaking about. It can be faunal data, it can be floral data, it can be primary data, it can be secondary data. It does not matter what kind of information, but what matters is that we are asking the right question and we have the right tools to be used to make sense of community information. For this, I will be using primarily the R package. R is a very interesting app that is used. It is openware. So if you have R installed on your computer, you know that you have R, which is the actual engine, and R Studio, which is the wrapper around R. And just to tell you all how to use or download R and R Studio, the basic thing is just type R Studio on your browser and you take the first link which goes to POSIT website. You click on this link and it opens the home page where you have two steps that you need to follow. You have to install R, which is the step number 1, and you then install R Studio. So you click on download and install. It takes you to the CRAN website where you can choose what type of R you want to download, whether you want to download it for Windows, for Mac OS, for Linux. And assuming that you have a Windows system, you click on Windows and it will give you this view where you again click on base and then it will show you the download page for downloading R, the latest version for Windows. You click this, it will download an installer in the form of a .exe package. You install this. Once the installation is complete, you can close this and then you can install R Studio. Once you have installed both R and R Studio, you can either find them on your desktop or you can find it on your start screen. As you can see it here, I scroll it till this end and I open R Studio. And this is how it looks. Very simple. On the left hand side, you have console. On the right hand side top, you have the global environment. That is, as and when you load files into the R environment, you will see this. And below you have various different widgets where you have the file widget, you have plots widget, you have packages, you have various other options here. Packages basically will tell you what are the additional tools or sources you need to do certain kinds of computation or visual interpretations within R Studio. You can think about packages just like the applications that you would install in a newly purchased phone. For example, when we purchase a new phone, we would not have all the required apps in our phone ready-made. So what we usually do is we install these apps going to Play Store or the App Store, depending on what OS you are using, and we will have different packages that we will be using. Now, before I begin with R, what is important is to give you all a background about what the data looks like. So if I show you how the data looks like, the data that I will be using for this presentation here. So I have this data set in Excel, which is basically a part of my PhD thesis where I have several rows and columns here. So if I zoom it here much closely for all of you to follow, you have X and Y, which basically are latitude and longitude. You have the year in which I have done the sampling or survey of my target organisms, which were ants. Then there is a column called HA, which basically represents what is the habitat. AG would mean agriculture, F would mean forest, LP is plateaus, PL means plantation, WL means wetlands, and so on and so forth. Then I have SE, which represents seasons. So PO in Goa would mean post-monsoon. Then when I scroll down, PR would mean pre-monsoon and W would mean winter. So these are the classification of different kinds of seasons. Then you have CD, which basically are codes. So each site that I visited had some unique identifier, which are codes. So there are different kinds of codes which are listed here. And then you have several of these right from the column G all the way till, there are several more. So these are basically short form of species. For example, TA_IN represents Tapinoma indicum. It's a particular species of ant. And here in this column, then you will see where all this particular species has been seen, whether it has been seen or not. All this information is there. So this information on this community is in terms of presence or absence. If I find a particular species in a given site, then it is 1. If I don't find a particular species, then it is left blank. So in this example, in the code, in the site which is coded 09AG, this species Tapinoma melanocephalum TA_ME, I have observed it, so I am giving it as 1. But I don't see this species, so I have left it blank. But I see Anoplolepis gracilepis ANGR, so I have represented it as 1. So this is how broadly the data set looks like. Here you can see this is the entire data set. I've zoomed out. It's a very big data set. So this is how this looks like. This is the community data that we'll be using initially to do all our activities. And please remember that this information is saved as .csv. CSV means comma separated values. Comma separated values are interesting extensions, useful extensions to be used because it reduces the file size. Usually community data tend to be very big, but if you save them in .xl or .xls or .xlxs format, then the file size is quite big. But if you save them in .csv format, the files are relatively smaller. They are only in KB size. So I'll go back to this our console, our studio console. The first thing I will do is open a new script or open a new page where I will do the actual coding. I'm assuming that most of you would be aware of certain basics of coding, the basics of how to go about doing a certain degree of coding. So I'm assuming that background information is there, and I'll proceed from here. So the first thing I would want to do is I would want to open the file of my interest here basically. So I would want to open the different files that I wanted. In this case, I want to open the file that I had shown. This is called Goa_survey_SF1. So the first syntax that I would be using is, let me just say that the name of my file is master.goa, and I assign this read.csv. Then I need to choose the file, so I will say file.choose, and I am going to tell the program that my Excel file has a header, so I will say header is equal to true. When I do this and I run this here, you will see that at the bottom select file option came. So when I click it, immediately the relevant folder opens. I select this and I say open. So the minute I have opened this, you can see that at the right hand side in the global environment, the file has opened. So you can see it's master.goa. There are 470 observations. There are 74 variables. So if you want to check what are the different heads or headers in this, you can say head master.goa. So I can just click this, and when I run this, At the bottom you will see that I've got this data set here, whatever we had seen in the CSV file, everything is there, but there is one difference or one change between the Excel file that we looked at in the CSV extension versus what has actually loaded on the RStudio environment. You see that all those blanks that have been kept on the Excel file have all turned into NA. So R kind of utilizes those blanks and fills them with NA. So the first thing that we need to do to clear our data file is to remove all these NAs and to substitute all of them with 0. So I will replace all NAs in my data with 0. Oops. Yeah, in my data with 0. So it will be like this. Yeah, it's going to be that. So if you look at it, when I put this hashtag symbol here, immediately the line has turned green. Hashtags are basically just like if you use social media, if you use Instagram, hashtag is basically a header. So hashtag basically is the connector, and here in R, when you put hash, that line becomes inactive. It is not treated as a code, rather it's treated as a descriptive line. If you put 3 hashtags here and you put another 3 here, you will see that immediately here, okay, you will see that immediately it becomes a header here, where you see that it has become a header, replace all NAs in my data with 0. So I can toggle with this up and down just like the contents of a book, which are hyperlinked. So if I have several lines or chunks of code, I can give these kinds of headers and I can toggle between different chunks very easily. So this is a very interesting shortcut that can be used within the RStudio environment. Now within this, I want to replace all NAs with 0. So the code is very easy. I invoke my master file as master.goa. I will use the drop down to avoid making any spelling mistakes. So I will say master.goa, then I will put the bigger brackets, and then I will say is.na. So the drop down has come. I'll select that is.na master.goa. I'll again use the drop down and I'll come out of it and I will say is equal to 0. What this code actually says is it asks the R environment to go within the file master.goa, and it asks the program to find out where all NA are present, and wherever NA is present to replace it with 0. So I select this, and if I want to check whether my data has actually been replaced with NAs or not, I can either just run the line number 2, or I can just double click here in the global environment and I can check. So I'll show you both. If I run the head of master again, you will see that all the NAs are now transcribed with 0, they're replaced with 0. If I click here as well, it will open in a new window, and then I can see that all the NAs are replaced by 0. So this is the desired outcome that I want. The next thing that I want to do is I want to subset all the community data information that is from the post-monsoon season, because my sampling was inadequate in other seasons, so I wanted to focus only on post-monsoon season where the sampling was done sufficiently. So I will want to subset. So let me again do this. I say subset data to post-monsoon. As I had said, when I click here, now you have those hyperlink chunks. It's very easy to go to the relevant chunks. So here I will say subset data for post-monsoon, and it is a very a simple process. It's a very simple process. I will say post-monsoon.goa, and I will say with master.goa, and I know from my data set that my post-monsoon data is from column number 1, to 277. So I select those relevant pieces of information. I select all those relevant pieces of information and I say go. So you can see that immediately on the global environment, I have the POM postmonsoon.goa data, which was for 74 variables, but now only 277 observations that are relevant to me. The next thing that we need to know is for any community data, cleaning of the data set is very important because often we have several variables, several information pieces that would not be important at a later stage. So initially we need to clean all our data set and we need to make sure that our data is clean. We have not made any mistakes in our data. So we have to do several kinds of data cleaning steps, which I'm not going to go into at depth, but I will just copy these codes here so that you can see, and I'll explain. What I want to do is I want to first replace all the row names by the site codes that I had mentioned earlier. Then I want to check whether in all the cells if there are any errors or not. So I want to check by mistake if there is any number which is greater than 1. So I check for all of those errors. I also want to check whether there are any sites which had no information. For example, I went to a site, I did not see any organisms there. So it is highly possible that in those places the entire column of species would be left empty, blank. So I want to remove those kinds of species as well. So I will use this special function called spec number, and I will run all of these to clear my data till the end. But as I said, our environment needs a lot of special packages to run certain kinds of analysis, and these are in this package. For our purpose, for our work that we are doing with respect to beta diversity, there are 4 important packages that are necessary. The package number 1 is tidyverse, package number 2 is vegan, package number 3 is add spatial, and package number 4 is rmis. So I will invoke all of these by using the function library. However, if you are using the R environment for the first time, you would need to install all of this. So you click the install button here, and you can install all of this by saying tidyverse, and then you can see that separate multiple with space or comma. So you say comma, and then you say vegan. So there you go, that is vegan. Then you say ADE spatial, so add spatial, and then you say comma rmisc, MISC, here it is. So you can select all of this and click on install, and all these packages will be installed. I'm not installing them again because I already have them installed on my system. But what I want to do is I want to load all of them. So I will do that by invoking this as library. I will say library, then tidyverse, then I will say library vegan, then I will say library, and I will say IDE spatial, then I will say library, and I'll type rmis, and I run each of these codes individually. As you can see, as I run them, they load, and you can see that they are loading in the console. Remember that once it runs, the blue color arrow will come here. Till then you should not do anything else. Yes, with this everything is run. Now I will run all the other cleaning procedures here. So basically I will put the code, site codes in the row names. I'll be checking for cells in the cell matrix and replacing errors. I will remove sites with all those areas which have no observations using spec number, and I will also drop levels to make sure that my data is clean. So with this I make sure that all my data is perfectly clean, and by that process I have cleaned all my data. Now the first thing that I want to do is to calculate species contribution to beta diversity. If you remember the theory explanation, different species will contribute to beta diversity differentially, and those species which are present exactly at 50% sites contribute most to variation between sites. This is what the logic or theory of beta diversity, the species contribution to beta diversity, is all about. Now, to implement this with an actual community data set that we have now imported, we will do the calculation here practically live. So I'll say calculate SCBD. If you would remember, that is a short form for species contribution to beta diversity. So let me give a name. For example, let me give the name as post monsoon beta dot overall, because I'm calculating it for all the different habitats without really wondering on where it is or where the site is. I'm taking the entire state as such, and the code is very simple. It is beta dot div. It's beta dot div. I select beta dot div from the drop down, and then I select the community data. So the community data is pom dot goa. POM.GOA is basically the cleaned version of it. But let us remember that POM.GOA, if I click here, you will see that there are lots of information that I don't need. For example, in my community data, to understand beta diversity, I don't need latitude, longitude, I don't need year, habitat, seasons, the code. I don't need all of that. I just need the species which starts from Tapinoma indicum all the way till Fidelgrive. So I need only the community information. So I need to select those rows which start from, I start from the column 77, and I start from the column 7, and I go all the way to the column number 77 here. That is part of the community data. 74. That is part of my data set. So I will accordingly code here. I will code here as, with the big brackets, I will say, comma, choose columns from 7 to 74. And the process does not end there. I need to also mention what kind of method that I am going to use for transforming this community data into distance-based matrices. So I will use the Hellinger method of transformation of data. So method is equal to Hellinger, Hellinger, and I am using only presence absence data. So I will tell the program to say that don't count the actual number of individuals there, only look at presence absence data. So the code for that is samp is equal to false, which means you don't count how many individuals are there, just look for presence absence, right? So this is the general code, and I will run this. So I have run this, and you can see that on the right hand side there is a list which is created, which is pom.beta.ov, that is post monsoon beta diversity overall, and there is a list of 8 items. If I open it, there are so many different things that are within that. And what I am, and I can actually open this, and I can see here you have the beta diversity that is calculated here, you have the SCBT that is calculated here, you have LCBT, the site contribution, the local contribution to beta diversity that we also spoke about in the theory sessions, and you have the probability based LCBT and adjusted p values, and you have all the various information sets which are here. Now here what I am particularly interested is to find out SCBT, species contribution to beta diversity. I am only interested in that. So I need to extract that information from the list. So it is very easy. First let me write a header, extract SCBD values. I'll say extract SCBD values. So let me give it a new name. So pom.scbd.ov. This is the name of my new file location, and I want the SCBD values to be saved as a data frame. So it's data.frame. I choose it as data.frame, and I say pom.beta.ov. This is what I want. Basically, this is what I have the list saved as, and I put dollar, and I want only SCBD, so I select the SCBD value here, and then I will run this. You can either use this or you can use the control and enter button to run it simultaneously. So now that I've run this, I can select this and I can say control enter, and you will see that the species contribution to the beta diversity of all individual species have been recorded as a data frame very neatly. So this is step number one. But what I also want is these species not just to be as row names, but to be a separate column as such. So what I am going to do is I'm going to assign the column of species by extracting information from row names. So I will just do this in here. I will just type this. I will say that within this file create a column for species and use the row names for that. And when I run this and when I again check back my file, I will see that there is a new column that has been created where the beta diversity values are on the left and what species belong, have that much contribution are on the right. So my data frame is more or less ready here to be utilized. But I also want to, kind of give the row names to it so that there is no confusion when I want to make any kind of, graphical representation. So I will assign names. So I will assign names of SCBD and species. So when I run this and I again check, I check for the header, I will see that the SCBD name has been prescribed here for the header and same with species has been prescribed. So this is the final data file that I will be using to visualize the contribution of various species to beta diversity. This will tell me which species contributes most to beta diversity. But before that, I would want to arrange my species contribution to beta diversity in a particular order. So I want to arrange them in an ascending order. So the syntax is very clean here. So I will say to convert all the species values as factors, and I would want them to be ordered in ascending order. So I have not put any symbol here. So I have not put a negative value here. So it is ascending order. So I have done that and I run this. So when I run this, it will automatically get arranged in the ascending order. The next thing is to plot the graph to visualize, and we use the function ggplot within the tidyverse universe to visualize this. So plot SCBD, that is what we will be doing. So the syntax is very easy. It is ggplot, and we will say data is equal to, so my data is equal to POM, my data is equal to POM dot SCBD. So this is what we have prepared. This is my data. This is what we'll be using. Then we have to define what are the x and y axes. So we will choose the AES function. We will say my y value is SCBD and my x axis values are species. I say this and then I say that my graph has to be a bar graph or a column graph. So I will say geom underscore call, and I will say that the position of all these columns have to be in stack. They have to be stacked one next to other very neatly, and I want them to be very thin. I don't want them to be very thick because width is equal to 0.5. So it will basically tell me what the width is. So let me just run this and show you how it looks like. So there you see at the right hand side the plot. So I will make this big, and I will also make this big. So you can see that there are various species and the contributions are listed here, but the x-axis is very cluttered. It's not very clean. The fonts are not very neat. So I will do some amount of thematic representation. I will do some kinds of cleaning. So I will not run through these codes one by one, but rather I will just kind of copy all of the codes that I had pre-written so that I make maximum utilization of the time. These codes will be made available for you to practice and use. So when I run this now, you can see that the function has run well, and immediately all the species that we were interested in, you can see that they are now arranged in an ascending order. You can see that they are all very neatly arranged, and you can see that the species which is being represented by the code OESM contributes maximum to the beta diversity. What this means is the species OESM, which is Echophila smaragdina, or the Asian weaver ant, very common species of ant which is found all across the Indian subcontinent. It's this orange color ant which makes nests on trees, usually mango trees, and you will find them more or less everywhere. So you can see that this Asian weaver ant, the Echophila smaragdina, it contributes maximum to beta diversity, and then the different species are contributing lesser and lesser. What this means is Echophila smaragdina contributes most to diversity of ants within my study area, that is Goa, which means when I take any two sites at random from Goa within my study area, it is Echophila smaragdina which decides the composition of the species community of that site. That is the species which is driving diversity. And as we had discussed in the theory session, how species which contribute most to beta diversity are very important in terms of conservation prioritization, because they give rise to variation. It is neither the most rare ones, neither the most common ones. The rare and common species don't drive diversity. It is those species that are there at about 50% of all the sites that you are studying. So that was the theoretical aspect of it, and this is the practical aspect of it. So even though R as an environment looks very daunting, it's a very simple and powerful tool to make sense of complex community data, and you can use this information for doing actual conservation based research in your academic ventures. So there are various ways in which you can again interpret this data for other kinds of purposes as well, but this is one of the basic frameworks that are available for doing species contribution to beta diversity. There are similar frameworks for doing site contributions to beta diversity, to look at functional beta diversity, functional group based beta diversity, functional redundancy. There are various other ways of doing them as well. So this is it for part 1 of understanding how to use the R environment and R studio environment to do basic community ecology with the beta diversity frameworks.